I'm Jonathan, and this is Mapped Learning, a place to learn freely without ads or noise. Let's continue our journey. In this video, I am going to be covering Internet Protocol version 4, otherwise known as IPv4. And this is the foundational knowledge that leads to all networking. The concepts that you will learn in this video will not only prepare you for full IPv4 addressing and later on subnetting, but also IPv6 and all sorts of other technologies. So in this specific video, I will be covering the binary scale, the powers of two, octets and classes, default, and what are known as CIDR Subnet Masks. The first time I saw that, I thought it was cedar, like wood, but no, it's actually cider, like apple cider. So, to understand IP addresses, you have to understand the binary scale. This is where it all begins. Binary is bi, meaning two, so we have in every single binary slot a 1 or a 0. 0 meaning the bit is turned off, or 1, the bit is turned on. And when we talk about numbers, as humans, we understand the decimal system 0 through 9, and then 10, which the numbers recycle. That's easy to understand for us. Computers don't understand that. They have to convert everything from decimal to binary. So we're going to do the same thing. So we start all the way at the right. In the English language and other languages, we move from left to right. In this case, we start at the far right and move left. So at the very right of the binary scale, we have 2 to the 0 power. Now, if you're not really into math, then 2 to the 0 power equaling 1 is kind of hard to understand. So when I'm writing down this binary scale, I start with 2 to the power of 2 because 2 times 2 is 4, and that's so much easier to understand. So if you're writing down this binary scale and you forget where to start, after you write down 2 to the 0 and then 1, 2, 3 all the way to 2 to the 7th to the far left, just start with 2 to the power of 2 equals 4. And then if you cut that number in half, 4 becomes 2, and then 2 cut in half becomes 1. Then when you move left, 2 to the third power is 2 times 2 times 2 equals 8. And then 2 to the fourth is 16, then 32, then 64, then 128. And we stop there. And the reason why we stop there is very important when we talk about IP addressing. And we'll get to that in the next slide. But for now, we'll just focus on 2 to the 0 through 2 to the 7th. And each time you increase a power of 1, you're adding another multiplication of times 2. So 2 to the power of 0, for whatever reason, is 1, but we'll go with that. 2 to the power of 1 means that there's just 1, 2. So it's 2. 2 to the power of 2, 2 times 2 equals 4, and so on. All the way 2 times 2, 7 times, is 128. Now, when we talk about an IPv4 address, we have what are called octets. The base of this word, octet, is oct, meaning 8. And we'll get to that in a second. These octets are comprised of binary numbers that we talked about before, ones and zeros. So before we move on, we have to understand some terminology. One binary number, a 1 or a 0, is called a bit. 8 of those in succession put together are known as a byte. So 8 bits is a byte. If you're familiar with the term kilobyte, that is roughly 1,000 bits. A megabyte is a million bits, and a gigabyte is a billion bits, and so on. It's not exact. We're just, with those big numbers, we're dealing with estimates. We'll get into the minutia of that later on. But for now, one binary number is a bit, and 8 of them put together is a byte. And just for little trivia, 4 binary bits put together is known as a nibble, not a full byte. That's a little bit of assembly language joking if you're not familiar with programming. So an IPv4 address has 4 octets, so 1, 2, 3, 4, separated by dots. 1, 2, 3. So 4 spaces for numbers separated by dots. And in these spaces, we put decimal numbers. That's where we get the dotted decimal notation. So you see in this example that I have in parentheses down here, 4 octets separated by dots, 192.168.1.1. If you have a home router, which 99% of the people on the internet do, you may notice if you log in, you have an IP address for your router that is similar, if not exactly this address. Now, if you have a router that is a combination modem, or depending on the vendor or your internet service provider, you may see something totally different. They may start you with a 10 dot address, and that's perfectly fine. It just means they implemented it differently. But a lot of home routers are pre-programmed with this address for the router. And this is an IPv4 address in dotted decimal notation. Now, a single octet, so we'll pick on this first octet, 192, that is an 8-bit number. So we write it out in a combination of zeros and ones in a particular order, and that becomes that specific octet. Now, if we move back to this slide, the way that we get 192 is that we take the first bit here and the second bit here and add them together. 128 plus 64 is 192, followed by a bunch of zeros. But that's just one example. We could have a totally different number. If we instead took 16 and 4 and filled in the rest with zeros, that would be 20, because you're turning the 16-bit on and the 4-bit on. The rest are zeros. You just add them together. So 192.168.1.1, those all break down into binary sets of 8 digits, 8 binary bits. A single octet can have a value all the way from all zeros, which would obviously be 0, to all ones. And if you add 128 plus 64 and so on all the way, you're going to get 255 in decimal. And the reason why that's easy to remember is because if you go to this scale, you double the number to get the next number to the left. So if we take 128 and multiply it by 2, we get 256. But if we subtract 1, then that's 255. So if we turn all of these bits on, it goes to 255. If we add one binary bit to that, it turns all of these bits off, and the next bit over to the left on, which is 256. So we have 0 to 255 in each of these octets. So we have 8 bits per octet and 4 octets total. That means an IPv4 address is 32 bits in length. And I know most of us know 2 to the 32nd power is 4.294 billion, right? Yeah, nobody knows that off the top of their heads like a calculator. So I used a calculator and got this number here. 4,294,000,000, blah, 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 blah. That is how many numbers are available in the entire IPv4 space, starting from all zeros to all ones in every 32-bit scale. Now, when we talk about IPv4 addresses, we need to understand classes. Classes are the basis by which all networking begins. IPv4 was first published in September 1981 for DARPA. And when they published IP version 4, they came up with these class rules. So when we look at IPv4 classes, we are only focusing on the very first octet on the left. So if we look at this previous slide, in the example of 192.168.1.1, we are looking at this octet here, and we are ignoring the rest of the 3. So we have 5 classes in total. We have A, B, C, D, and E. A, B, and C are specifically used for host addresses. And when I say host, I mean networking devices. What constitutes a network device? Well, anything that can be used on a network. We have routers, we have switches, we have computers, phones, printers, anything that communicates on a network, TVs. It can have a host address on an IPv4 network. Class D, if you look at the last column here in this table, we have what's called multicast addresses. Now, I'm not going to talk about that right now. It's very complicated, but this just means mass communication. And that's what Class D is used for. And for Class E, we have experimental and reserved. And if you're an 80s, 90s kid like I was, back in the day, we used to also call these governmental addresses, but that's not really used anymore. So we just use experimental and reserved. When you are looking at these classes, they had to figure out how to take all of these networks and divide them in a logical way. So they came up with these rules. And here's how the rules work. For Class A addresses, when you're looking at the first octet, the very first binary bit on the left must be a 0. So if we're looking at this scale at the bottom, we're talking about this bit right here, where the 128 is. This binary bit must be 0. So what does that give us for a range? Well, we have the lowest number would be 8 zeros, which would obviously be 0. If we added all zeros together, we get 0. However, if we do 0, 1, 1, 1, 1, 1, 1, 1, what is that? Well, remember what I said before. If we have a bit on and the rest zeros, if we subtract one binary bit, it turns that bit off and the rest are ones. So this 128 bit is off, the rest are on. That means that it is 127. So you can see in the range here you have 0 to 127. Then we have class B. The rule for class B is the first binary bit must be a 1 and the second binary bit must be a 0. So let me go ahead and erase my mess here. If we have the first binary bit is a 1 and the second binary bit is a 0, the lowest address would be 1 followed by a bunch of zeros. So if you add 1, 128, and 0 of the rest of the bits, well, the first number is 128. And then if we take 1, 0, 1, 1, 1, 1, 1, 1, since the 1 and the 0 are locked, if you add all of these numbers together, 128 through 1, and not including the 64, that would be 191. So if the first octet is anywhere between 128 and 191, then it belongs to class B. The rule for class C, the first 3 binary bits must be 1, 1, 0. So the lowest number there is 192, and the highest number would be 110, 111 to the end, and that would be 223. D, similar rule. The first 4 bits would be 1110, which would be 224, and then 1110 followed by 4 ones is 239. Now class E is a bit different because it has to fill up the rest of that octet range. So the rule in this case is the first 4 binary bits must all be ones. So 1, 1, 1, 1, meaning that the lowest number is 240, and then the highest number, as we discussed previously, all ones, is 255. So that is mathematically how you get the 5 different class addresses. Again, I must reiterate, that is based on the very first octet, nothing else. When we talk about these classes, we also have to talk about default subnet masks. Now, subnet can mean 2 different things. Subnet can mean network at large, or it could mean a small subset of that larger network. I will talk about that in another lesson, but not here. Right now, we are just going to work with default subnets. So if we take the previous slide and we convert that into default subnet masks, we can only look at the host address networks, classes A, B, and C. Remember, D is for multicast, E is for experimental and reserved, so we can't use those. So for class A, B, and C, we have default subnet masks. And I will give you an example of each. So we remember that Class A addresses have a range of what? Do you remember the rule? The rule is that the first binary bit must be a 0. So the range is anywhere between 0 and 127. So I can pick any number in between 0 and 127 in the first octet, and that will be a Class A address. So just at random, I will pick 16. So 16 dot whatever dot whatever dot whatever. Okay, that is a Class A address by default. The subnet mask is also in dotted decimal notation, but we write these numbers differently. If you are looking at the binary scale, a subnet mask has bits turned on from left to right. So from the largest number to the right, lowest number, in sequential ones. And then once we turn a bit to a 0, all of the bits after that are 0 as well. There are no mixing and matching. It doesn't go 111 0 0 0 1 1 1 1, and we don't start all the way at the right. If you look at the bottom table, we can see this graphically. So the default subnet mask for Class A, we write it down below, is 255.0.0.0 for Class A. Now, I like the documentation that Cisco gives for understanding subnet masks. The reason why we call it a mask is because we mask those bits as being important. We don't want them to change. It's like putting a mask on those bits and never changing them. So when we look at this 16 dot whatever whatever, wherever the bits are turned on, that means that all the bits for that address are dedicated to the network. So we're saying every bit in this 16 address is important. So they need to be locked in place. So we can just draw an imaginary line right there. Everything to the left of this line is part of the network, and everything to the right is a host address. So 16 dot whatever is all going to belong to the same network by default. That doesn't happen in practice, but we're talking about a technology that is over 40 years old. So back in the 80s and 90s, we didn't worry about networks having massive numbers of devices. It wasn't until the internet came around that obviously we started running out of addresses. I will discuss in further lessons how technologies put a pause on the need to get rid of IPv4 addresses, but not right now. So those are Class A addresses. Class B, if you remember the rule, the first binary bit is a 1 and the second binary bit is a 0. We have anywhere between, now I forget, 128 to 191. Thank you, slide, for remembering math for me. So I am just going to pick a random number. We'll make it easy, 128. 128 dot whatever dot whatever. And remember, this is just mathematically an example. So the default subnet mask for this Class B is 255.255.0.0. So I kind of drew it like that. So if you look at the first two octets, we have 255.255. That means all bits are turned on. So everything above those are locked in place. So every address from 128.0.0.0 all the way up through 128.0.255.255 as an address are on the same network. Same thing for class C. The defaulted mask is 255.255.255.0, and an example of that would be the 192.168.1 network that I spoke about in this slide, like your home network. Now, a couple things that I want to talk about in this slide before we get to the next one. Here in this column, we have that CIDR notation. I will explain what that means in the next slide. But what this tells us is how many bits from the far left into the IP address is turned on for the network. And for default, Class A is using 8 bits for the network, which is why we have 255 in the first octet. Class B is 8 plus 8, so that's 16. And Class C is 8 plus 8 plus 8, which is 24. Now, I am just going to tell you up front here, when I first created this table, I made a mistake. So if you're one of those people that understand networking and you look at that 255 as number of networks and say, wait a minute, you are totally wrong. Thank you for correcting me. The number of networks here is actually 256. So there is a formula on how to determine how many networks are available in a particular network and how many hosts per network are available as well. So down at the bottom, if we look at X is network bits and Y is host bits in a subnet mask, we have two formulas. Networks is 2 to the power of X, where X is how many bits are turned on for the network. So if we look at class A, the CIDR notation is /8, meaning 8 bits are turned on for the network. So in a class A, we take 2 to the 8th power, and if we remember from this scale here, we don't have 2 to the 8th here, but if you imagine doubling 128 to 256, this right here would be 2 to the 8th power. So that's why we have the number of networks here as 256. The number of hosts per network is 2 to the power of y, which y is the number of hosts, number of bits in the host part of the subnet mask, minus 2. Why do we subtract 2? Well, in each network, we have 3 different types of addresses. And I'll get to exactly how we define what those are. But those 3 types of addresses are the network ID, the host range, and the broadcast address. When we are assigning IP addresses to hosts, we cannot give a host address either the network ID or the broadcast address. That's why we subtract 2. So if we look at a class A, 2 to the power of 24, because that's how many bits are in the host section of this default subnet mask, and subtract 2, we get 16,777,214 available hosts per network. Now, obviously, As I stated before, we don't use that many hosts per network, but this is just a theoretical exercise. If we look at a Class B address, we have 16 bits for the network and 16 bits for the host. And you can see right here, 2 to the power of 16 is 16,384. If we subtract 2, then it's 16,382. Likewise, with Class C, we see here the difference between 2 to the power of 24 and 2 to the power of 24 minus 2. That's why these numbers are different. And then 2 to the power of 8 minus 2 being 254 is much more manageable, which is why most network routers, home routers, are pre-programmed with the 192.168.1 network address, because they can have a bunch of addresses and they will all be similar, so you can work with those much more easily. So that's how default subnet masks work. Now, as I mentioned in this top table, the CIDR notation. Well, what is CIDR? CIDR stands for Classless Inter-Domain Routing. All 4 of those words are extremely important, which I will not cover right now. I will cover in a future episode when I talk about subnetting. But just remember, CIDR means classless inter-domain routing. Now, the notation. If you were a network administrator long ago, back when dinosaurs roamed the earth, writing down an IP address with a subnet mask of 255.255.255.0 a whole bunch of times on a network map, that just got to be way too much writing. So what they did was they came up with a way to write shorthand network to any address, and you would automatically know how many bits were being used for the network, which is exactly how you get these CIDR notation numbers in this column. You just count from left to right how many bits are turned on for the subnet mask, and that is the CIDR notation for that address. So I have some examples here. The first one is 192.168.1.15. By default, that is a Class C, so 24 bits are turned on, 8 plus 8 plus 8, for the network. Now you see in parentheses here, this is a host address, and that is exactly right. For this address with the CIDR notation of 24, this is why we have to subtract 2 addresses from that available host range. The network ID is anywhere in the subnet mask you see a 0, you make all of those zeros. So if you draw this imaginary line right here, everything to the left of that imaginary line stays in place. You don't change it. Everything to the right, to get the network ID, you turn all of those bits off. So in a default subnet mask, when you turn all the bits off, you get a 0. That's why 192.168.1.0 is the network ID. Then, to get the first available host address, you add 1 binary bit. So 1 binary bit added to 0 obviously is 1. And we add 1 binary bit from the far right, not from the far left. Later on, when I talk about subnetting, this will make a lot more sense. But for right now, just understand, when you add 1 binary bit to 0, it is a 1. So the first available host address is 1. And then to get the last host address, I always skip ahead to the last address because it's easier to calculate. But when we turn all of the bits on in a particular octet, that is 255. So that is this example right here. That is the broadcast address. And a broadcast is when you send network communications to every device in that network. And that is a special address. If something sends a network communication to a broadcast address, all network devices know that it pertains to every device in that same network. So to get the last available host address in that network, we take the broadcast address and we subtract one binary bit. So one binary bit subtracted from 255 gives us 254. So that's your host range. Everything in between can be assigned to a host device. And it doesn't matter in which order you assign those addresses. It just doesn't matter. You just have to remember, do not assign the network ID or the broadcast address to any devices. No device will actually let you assign those two reserved addresses to that device. So that's how you get your host range. Now, if we take this broadcast address of 255 and we add one binary bit, well, 256 doesn't go into an octet. And just like in decimal numbers, when we go from 9 and we add 1, well, there is no single digit that you can add to 9 and get the next number. So we have to change that number to 0 and carry the 1 over to the left. Similar with this. When you add one binary bit to 255, all the numbers, all the bits turn off, so we get 0, and then we carry the 1 bit over to the next octet to the left, so we add 1 to this octet right here, and that becomes 2. Now, we still have that same imaginary line right here in between the 192.168.2.0. So any address that has this 2 in there is on a different network than the 1 network above it. So just remember, when you have a 24-bit mask, the first 3 octets are locked in place, and any number that's different means that it is in a different network than another address that has a different number. Now, it gets a little bit more complicated from here, but I promise you, if you stick with this, it will make more sense. I have many students that can attest that my way of teaching IPv4 addressing and subnetting is much easier than traditional IPv4 addressing courses. If you were a network student long ago, you may remember the subnetting manual that was pages and pages in thickness with a bunch of examples that was infinitely difficult to understand. So I came up with my own way to teach it, and this is what I came up with. So please understand that it will get easier from here as long as you follow along with what I teach. So thank you for being here. If this helped you, please share it with someone who's learning too. Everything I make is free, and everything that I teach from is my own creation. These slides, my Substack, all the content is my own. If you'd like to support the mission and keep all of this knowledge free, the links are below. I would appreciate if you like this channel, please donate to my Patreon or my YouTube, and I'll see you in the next one.